Thank you very much. Thank you to the organizers for this event. So I will speak about the Gibbs states of the Ising model, first in the nearest neighbor setting and then in the long-range interaction setting. I just should say that this is an off-critical talk, so it will be, all the results will be for low temperature, sometimes very low temperature. So, okay, we'll not go through the critical point. I will start to settle the notation with a few definitions. So, I fix a finite volume lambda in ZD, and to each point x. Sorry, here. To each point x, the spin is denoted sigma x, and the Hamiltonian of the Ising model is this one. So the coupling constants between x and y are denoted gxy, and I will focus to the ferromagnetic case where gxy is positive, although sometimes some results will be possible to extend to the non-ferromagnetic setting. So of course for this model to make sense, I should enforce this hypothesis on gxy, the fact that they should be summable for a fixed x and varying y into the whole ZD.
What's W? Wy?
Omega.
Omega. Okay, what's omega?
Here? Sorry, so maybe, yes, I should say. So around the finite volume, I will put a boundary condition, which I will call in the whole talk omega, little omega. And large omega is the set of all configurations, plus minus ones to the power ZD.
And it's translated invariant, so gxy is only.
This is like this. Afterwards, yes, of course, I will take translation invariant coupling constants, but for the moment, it's general. So this is the Hamiltonian with boundary condition omega in the finite volume lambda for a configuration sigma. And the finite volume, so the Ising measure in finite volume is this one, it's beta positive. And I will get interested in Gibbs measures, which can be defined as the convex hull of weakly emitting states. So if you take mu omega lambda as before and enlarge lambda to go to the whole ZD, possibly varying omega at each step if you want, then you take a weak limit in the sense that set of measures mu n converge to mu if the expectation of all local functions converge. Then you end up defining this set G beta, which is the set of Gibbs measure at inverse temperature beta. And this is very interesting object, which is a simplex, and which in general is very hard to describe. So just for definition, so the critical inverse temperature in this setting is the supremum of the beta such that there is a non-uniqueness. So such that, okay, the supremum of the beta such that you have only one such infinite volume Gibbs measure. Yes, sorry, I tried to mimic a blackboard, but it's maybe not the best. Okay, so this will be the definition of beta critical. Just a few definitions such that things are clear. A measure mu in G beta is said to be extremal if whenever you try to decompose it onto other two measures, then the decomposition is trivial in the sense that if mu is lambda nu 1 plus 1 minus lambda nu 2, then mu coincides with nu 1 and nu 2. And also mu is said to be translation invariant if it gives the same expectation to any local function, and that translates by a translation of ZD. So now what I will call in the whole talk the Brughin state, it will be such a state which is extremal and non-translation invariant. So we'll see some settings where such states exist, and some results where we can exclude the existence of such states. So first of all, I will focus on nearest neighbor interactions. That means I take gxy being just 1 if x and y are neighbors, and 0 otherwise. So of course you know that in dimension 1 there is no phase transition, beta c is infinite. And in dimension 2, so there is a phase transition. Okay, this means that beta c is non-trivial, strictly in between 0 and infinity. And it was a result in the 80s, but in 2 different independent papers by Eisenman and Higuchi, that G beta is actually the simplex, which is given by all the convex combinations of mu plus and mu minus. Mu plus is the state which is obtained as a limit of plus boundary condition, all pluses around the box, a finite box, and take the box to infinity. And mu minus is the same with minus sign. So what does it mean? Okay, so this is for large temperatures. At large temperature you have uniqueness, and below critical temperature, okay, you have non-uniqueness. But what does it mean? This result is that locally what you see is you cannot see more than either mu plus or mu minus. So locally, every local function sees a pure phase. And so the archetype in the nearest neighbor case in 2D that you should have in mind is, if you want to create something else than a pure phase on a local level, you can try to impose the existence of an interface. So you can take a plus boundary condition above a box and minus below, and see how does this interface behave. If it fluctuates, then you will see a pure phase in the middle. If it doesn't, then you see something else. And so the archetype in dimension 2, so it was proved first by Galavotti and then by Greenberg and Joffe, is that in the box of size n, such an interface, which is usually called a Dobrushin interface, has Gaussian fluctuations. So in a box of size n, the typical fluctuations of such an interface are for the square root of n. What does it mean? It's something what I just said in a sense, is that if you take the limit or subsequential limits, if you cannot prove that the limit exists, of such finite volume measures, then the interface fluctuates. So in the middle you see either the plus phase or the minus phase, and by symmetry you see with a factor 1/2. So for half the configurations you see plus, and half the configurations you see minus. So in fact in the infinite volume you see the convex combination 1/2 mu plus plus mu minus, which is translation invariant. So it tells you that in this setting G beta contains only translation invariant states. And I want to say also something which will come afterwards in the talk. We can focus on the magnetization profile. That means, in fact, you can move along this line here from bottom to top along the box and measure what is the average magnetization there. And so it's a posteriori, it can be seen as a consequence of some other results, but it was first a result by Abraham and Reed in 76, is that when you scale the height by square root of n, so you take sigma at height so this this coordinate is 0 and this one is s times square root of n. Then in the limit n to infinity, you get a Gaussian profile. So you get m star, which is the magnetization at temperature beta, the sign of S, which tells you that above it's plus and below it's minus, and here it's the cumulative density function of a Gaussian with a variance that is explicit and depends only on the temperature. So this magnetization profile was found by transfer matrix tools at the time. And okay, so this is the setting for the 2D nearest neighbor model, and I just want to give a result that we proved with Ivan Velenik in 2012, which can be seen as a finite volume analog of the Eisenman and Higuchi theorem, which is valid for beta larger than beta critical, so for in the subcritical phase, in the whole subcritical phase. So if you fix positive epsilon and you take your favorite boundary condition omega, then what you can do, you can measure the difference between the expectation of any local function living in the box of size n to the power epsilon, so something diverging with n but very slowly, so something containing all the local functions. So we can measure the difference between the expectations of such functions and the convex combination onto the pure faces. And the statement is that, so for any boundary condition fixed that you choose, there exists an alpha which depends only on n, omega, and beta, such that this difference is of order n to the power minus a half plus epsilon. And this, I will try to, just in a few slides, to give you the ideas of what happens, because it's a finite volume proof and it's kind of easy to explain.
Is there a matching lower bound also to explain that?
Yes, in fact you can find some functions, for example sigma 0, that would achieve n to the power half. So this is just the idea of the proof. I will somehow cheat in several points, but it's just to give you the idea of the proof. So the first step, if you take the boundary condition, your favorite boundary condition around the box, these little things are sign changes, let's say, around. Then the first step is to say that the interfaces that cross the box of size half, n half, have opposed endpoints. What it means is that this line here, joining x to y, if the interface crosses, okay, so maybe I will say it like this. If you have two endpoints, x and y, such that the interface between them reaches n lambda to the n over 4, then the endpoints, the line between the endpoints should intersect the box lambda n over 2. If this is not the case, in fact, so this statement will be true with probability exponentially close to 1 as n tends to infinity. And why? Because, in fact, below the critical temperature, you have exponential decay of correlations. And so if this is not the case, so if x and y are not opposed, here in the sense I just defined, then the interface enforces a path of plus spins from x, let's say, to some point z in the little box, and so the interface should pass through some z around this little box. So in fact, you can upper bound the probability that this happen by the number of points around the little box and of size n/4 times the price you pay to get an interface which makes such a triangular deviation somehow. And what you pay is the surface tension between x and y, but you have to retract the surface tension between x and z to y. So in fact, you get an exponential cost, which is the surface tension between x and z plus z and y and minus x and y here. And of course, for beta larger than beta critical, and such a hypothesis on x and y, this is exponential in n. So the first step is somehow a cleaning, which tells you that if an interface is coming to the middle, then the endpoints have to be opposed. And the second step is to say, okay, so let's take some such interfaces such that the endpoints are opposed. You can build several of them, but in fact, the number of crossing interfaces are either 0 or 1. Why? Because if you have more than 1, let's say 2, then the cost to make them cross is higher than the cost to link them like this, like I wrote in little dots here. So in fact, also with a probability that is converging exponentially fast to 1 as n tends to infinity, the number of such crossing interfaces is either 0 or 1. So if it's 0, then you are done somehow. In the middle, you are in a pure phase. And if it's not the case, so you have only one interface. And what should you do if you have one interface crossing? You have to go deeper in the two-point function, in the asymptotics of the two-point function, to say what happens in the very middle. So does this interface achieve going to very far to the middle, to such that a local function can probe it or not? And in fact, if you use not just the exponential decay of correlation, but the Ornstein-Zernike asymptotics of the two-point function, then you can prove that if there is an interface which is crossing, then it crosses a box of size n to the power epsilon with a probability that is only n to the power epsilon minus a half. It's the same kind of argumentation than for the first step, but going deeper in the asymptotics of the two-point function, because the exponential cost now can be only bounded by 1, and you have to see the prefactor and to see how you gain. And so there are two, 1 over square root of n above, 1 below, and so this is exactly somehow this is reminiscence of the Brownian scaling of the interface. So these are the three steps which tell you why you have Eisenman-Higuchi theorem in dimension 2 for nearest neighbor interactions. And so the G beta is described for dimension 2. In dimension 3, what happens is that you have localized interfaces. It means, so at least for beta very large, the Brushin proved in the 70s that in a box of size n, the typical fluctuations are of order 1. That means that interfaces are localized, and so you have more than translation invariant states in your G beta. At each height, you have one state in the G beta for Ising dimension 1, in dimension 3. So in other words, the limiting states mu plus minus, like this, when n tends to infinity, is non-translation invariant, and it's also extremal for each height in each yeah, for each height.
So and here you can also put them through at rational angles or something if you're...
This will fluctuate. It depends the slope, of course. What you can do, so is with okay, if you take maybe one step, then what you will see from above is an effective two-dimensional system, and this fluctuates. So we'll see a convex combination of two heights.
But if you take rational
and rational,
angles, if the beta has to be larger depending on the angle, something like that.
Well, I guess it fluctuates for the square root of n. Or
you can't take an angle. It's supposed to be rough.
Yeah, it's rough. Yeah, it will fluctuate of order. I guess square root of log. If the angle is
it's nearest neighbor, yeah.
Yeah, it's nearest neighbor. Yeah. So that's why, in fact, these states are believed to be the only ones which are extremal and non-translation invariant.
So it depends on being nearest neighbor. If it's second neighbor, then you can say what angle.
Second nearest neighbor. I will afterwards. I will talk about long range. So it will be infinite range. So second nearest neighbor, I have to think. But in fact, I think it will be rough also. Because any finite, I think any finite range interaction will be rough also. Okay, so this is, let's say, the state of the art for the Ising model nearest neighbor dimension 1, 2, and 3. And I will pass to the long range setting. The definition for me will be this one. So I take the coupling constant between x and y to be 1 over the distance between x and y to the power alpha. This, of course, makes sense only if alpha is larger than d, as I said in the beginning. And you will see some of the arguments I will give can be applied to a more general form of long-range interactions, but let's fix to this definition. So what happens in this setting? So in dimension 1, it's already a very interesting model, which has a phase transition for alpha in between 1 excluded and 2 included, but not for alpha larger than 2. So this was originally proved by Dyson for the whole range of alpha except 2, and then by Fröhlich and Spencer in 82 for the case alpha equals 2. So in fact, in dimension 1, there is a very interesting feature of this model at alpha equals 2, but I will not elaborate on this, just to say that there is a first order phase transition here for this point, and also there is a Kosterlitz-Thouless intermediate phase at this point, and this was the content of this paper. But still, what happens, so somehow I want to give also this message, is that the long range setting has some features which are similar to the nearest neighbor case, but one dimension more. And here it will be the case. The fact is that there are no Dobrushin states, and so there are no. I recall what it is. The Dobrushin state is an extremal non-translation invariant state. And why doesn't it exist in dimension 1 long range? It is somehow, it comes from a series of papers by Cassandro, Merola, Ferrari, Presutti, Pico, some other people I also forget, I guess. They achieved to get the magnetization profile of this model, of the long-range model, and to to see at which scale does the one-dimensional interface fluctuate. First, they define what is the interface point in dimension 1, and then they say at which scale does the interface fluctuate. So the setting is that you take a box, one-dimensional box, and take the Brushin boundary conditions. That means all pluses above and all minuses below. And one result of their paper is that the typical scale at which you see the magnetization profile change is at this scale, which is, I should have put some graphic, but in fact the scale interpolates between, so for alpha, let me think, at least it should interpolate between, for alpha equals 2, the decay is large enough such that you have the nearest neighbor feature, so you have no phase transition. You should have the interface which takes the whole box, which should be fluctuation of order n. And for alpha equals 1, you scale down to Gaussian fluctuations. So this scale goes from 1/2 to 1, as alpha goes from 1 to 2. And what is nice also is that the magnetization profile is the Abraham-Reed profile when you rescale by this quantity here. So somehow, in the long-range setting in dimension 1, is very similar to 2D nearest neighbor, but at another scale, which interpolates between 1/2 and 1, somehow. And this series of paper used cluster expansions and can be proved for alpha, which is close enough to 2, but in fact is conjectured to be the case for all ranges of alpha. And what happens in dimension 2? So as I said, this should some behaviors of the long-range models are similar to nearest neighbor and one dimension more. But is it the case in dimension 2? Not quite. Of course, there is a non-trivial phase. So there is a phase transition because there is phase transition in dimension 1. So you can, by correlation inequality, you still have phase transition for dimension 2. And what we proved a few years ago with Ernaut Valenta, Arnaud Leny, and Violetta Ruszel is that the Brushin states do not exist for the two-dimensional long-range Ising model for any alpha and any beta, which means that, in fact, so morally interfaces fluctuate. You don't have extremal non-translation invariant states. And I will just give you the idea of the proof, which is structural in the sense that we exclude states which would be at the same time extremal and non-translation invariant. So how does...
In the sense it's not the same as one dimension more.
It's not the same, yeah. I forget. I asked the question, is it the same? And the answer is it's not the same. In this respect, sometimes it's very in some respects it could be the same as nearest neighbor in the one dimension more, and sometimes it's not. And yeah, I cannot say for which features it matches, for which it doesn't, and okay, it depends. Here for dimension 2, it doesn't. Okay, so the proof idea is based on relative entropy method. So we compute the relative entropy between a state which has an interface at height 0 and a state which has an interface at height 1. On the picture here, this is height 0, this is height 1. And what I call mu plus minus 0 n is the measure which has pluses all above up to height 0, and minuses below. And what I call mu plus minus 1 n is the measure which has a spin flip here at height 1. So the argument goes as follows: how do you calculate the relative entropy between those two states? So by definition, the relative entropy is the ratio of probabilities under this measure and this measure times the log of this quantity, and you take the expectation in this state here. And the point is that so first you can take a square box, dimension n by m, and if you let first m going to infinity, that means going working in the strip here of length of width n, then this relative entropy is just the average energy difference of the configurations with boundary condition 0 and with boundary condition height 1, expected in the state at height 1. So this is something very easy to calculate. You just have to compute an expected energy difference. And how do you compute it? So, in the Hamiltonian you have the sum of jxy, sigma x, sigma y. And you have to compare those two Hamiltonians. So the only terms for which these two quantities differ, it is when x is inside the box here, and y is here in this shaded white region. Why? Because other terms, for all other terms, this quantity will match with this one. The product of the spin will be the same. And well, it tells you that this quantity is exactly sum over x in the box and y in this strip of the distance to the power minus alpha times the expected spin at x. And so maybe I can comment something here. If you stop here and just say, okay, sigma x is less than 1, then you have to compute such a double sum, which is morally x is in a box of two-dimensional size. So this is a two-dimensional sum, and this is a one-dimensional sum because y is on this line. So if I just say that sigma x is less than 1, then this will be a convergence series when alpha is larger than 3. And this also doesn't depend on the sign of the interaction. So even if it's antiferromagnetic, you have that for alpha larger than 3, the relative entropy between those states is bounded. But I want to go all the way to alpha larger than 2. And to achieve this, I have to use the ferromagnetic character of the interactions. And in the ferromagnetic case, you can observe that this quantity, so the average spin at x, here the average spin over, if you fix y, let's say, then you have any spin here which has opposite magnetization as the spin here. So somehow you have a cancellation due to the ferromagnetic character of the interaction, which kills you one sum here. So in one step more, what you can say is that by symmetry and then upper bounding sigma x by 1, you end up with a double sum which is only two-dimensional. X will live here in the red region, and y will live in the white region. So it's a double sum with two morally one-dimensional summations, and so this is up to a constant. It decays like n to the power 2 minus alpha. So it's bounded for any alpha larger than 2.
Loren, why do you say you're using ferromagnetic? So it seems you're using just a symmetry. Why does it matter ferromagnetic or not?
Because you should ensure that sigma x here, so the average magnetization here is the opposite as this one. So, I mean, it would be more difficult in the, if it's not ferromagnetic, you...
Look, just naively looks like something should be more.
Yeah, it's yeah.
But I just to get some intuition, if one pretends that it's a continuum and just tries to calculate the surface tensions, then it's the same sort of integrals that come in, and you conclude that that's finite. Is that sort of morally equivalent? Yeah. You
mean if I replace by an integral here?
Yeah, but I guess it's a somewhat different. Well, I guess I don't understand this relative entropy enough. But if I just do a very naive calculation, I put a surface interface with a slight curvature in it, and then calculate the energy of that and see if it's proportional to 1 over the curvature squared, just by doing the integrals over the long range part.
Yeah.
And then that's finite. That's the equivalent statement.
The tail of the integral you speak about will be the same. Yes.
Yeah. Okay.
Yeah. Okay. If I understand correctly, yes. So yes. So this is just to say that with this trick, we can go up to alpha larger than 2, and so exclude the Dobrushin state up to alpha larger than 2. I just have another slide to explain the argument, which is originally due to Brikmont-Leibowitz and Pfister. It's very general, and they have used it to prove equivalence of boundary conditions in several settings, but here we use it this way. So we have computed the relative entropy between mu plus minus at height 0 and at height 1. What we have proved is that mu at height 0 and at height 1 are mutually absolutely continuous because of this relative entropy bound. And thus, they have the same states in their extremal decomposition. This is if they are absolutely continuous, you have no other choice. And thus, if one of them is extremal, then it's equal to its translate. And thus, it's translation invariant. So it's more, this argument is more of a structural statement, is that we exclude states which are at the same time extremal and non-translation invariant.
Isn't this a bit paradoxical? Suppose that I take alpha equals 1000, then I would naively say that I'm very close to nearest neighbor situation. So what's going on? Why?
Nearest neighbor in dimension 2.
No.
But here we are in dimension 3.
No.
2.
It's still 2, okay.
Yeah, that's yeah.
Okay.
So you have to compare, For alpha large, yes, indeed, it's close to nearest neighbor, but nearest neighbor in 2D, which is the Gaussian.
Sounds good, thanks.
Okay, so this is the spirit of this result, and of course it doesn't go to the Eisenman-Eguchi statement. It doesn't say that G beta is only containing translation invariant states, because okay, with this simple somehow argument, we cannot say that that there doesn't exist other extremal non-translation invariant states. But morally, nothing else could happen that an interface which would be enforced in such a way. That's why also I talk about this finite volume Eisenman-Eguchi result before, is that somehow you could say to get the Eisenman-Eguchi result, what is missing is to take the favorite boundary condition you want and perform energy estimates in such a way that you can ensure translation invariance of the states. But of course, it's very difficult in the long-range setting. And I want to finish with an ongoing work with Romain Durand in Grenoble and Violetta Ruszel in Utrecht. It's something that is using this kind of tools to go towards the magnetization profile of the long-range Ising model in dimension 2. What we are close to be able to prove is that so the relative entropy between the states which have interface at height 0 and at height n to the power delta. So I shift, so the interface now is not at height 1 but at height n to some power delta. The relative entropy between these states, in fact, it's not exactly of these measures, but on their behavior in a box of half the size, let's say. This relative entropy will be bounded if delta is smaller than a certain exponent and infinite otherwise. And this exponent is exactly the one given by Fröhlich and Zegarlinski in 91, which is okay, this is a paper about the 1D integer value GFF with long-range interactions, which is actually a model which is conceptually very close to our model for very low temperatures. So in this paper, they treat the one-dimensional integer value GFF with long-range interactions and compute the fluctuation exponent of this model, which is this one. So the gamma is the minimum between alpha minus 2 over 2 and 1/2. This time I put the graph. It's an exponent which interpolates between 0 and 1/2, and the 1/2 is achieved at 3. So it joins your question here. We think that starting at alpha equals 3 and above, we have Gaussian fluctuations. And what should I say about this? Yes, somehow it's kind of, so it's...
Do you think below that is not Gaussian, or it's Gaussian but just with the different...
yeah, we don't have the... You're right, so it doesn't say that the profile is Gaussian, but that below this exponent, the measures are absolutely continuous with respect to each other. It's not the same, I agree. Yeah. But so this bound would be used to say that at least you have fluctuations, and Dobrushin state, of course, do not exist because interface fluctuate. And I just want to stress that, okay, the kind of result we can get is not very precise and go to Eisenman-Iguchi and so on, but I think the positive point is that the tools are kind of soft somehow, and we see exactly where this transition happens. Somehow here it's the region where the long-range interaction matters a lot in the system. And after alpha equals 3, then you see that no matter the long range, it's the nearest neighbor that is the leading term, the leading order. So with this kind of relative entropy estimates, we see that very clearly. This crossover somehow, and. Yes, and okay, and this can provide a lower bound on the fluctuation of the interface in the long-range setting. I don't know if I am late, but thank you.
What is the state of the understanding of 3 dimensions above the roughening transition?
We can perform such an argument to exclude the Gaussian states above some certain alpha, but I think it's not the optimal one. If it's you mean nearest neighbor?
It's three dimensions.
Yeah, three dimensions.
I don't think
Then-
I don't think.
Yeah.
Sorry, what do you exclude in 3 dimensions?
No, it was for long range setting. I didn't get
Three
the-
dimensions at intermediate temperatures between the roughing and transition. It's not. That's not. Nothing included in there.
Yeah. So this
So
was
one might
for-
think that if you make alpha equals any alpha less than 4 in 3 dimensions would mean that you can't have that you can get
exactly.
push states all the way up to the transition.
Yeah.
Van Beeren had an argument for proving the dilution phase for the temperature which is below the critical temperature. And is that work for this case also in 2 dimensions?
Is that what is the question? So indeed, the Van Beeren provide a proof of.
The Van Beeren's argument works for in the case of long range things, but you have in a 2-dimensional system.
Yes, yes. So what we can do with this Van Beeren proof is that cook up some states which which how do you say?
Basically, what you showed was that it doesn't work for isotropic interactions.
Yeah, exactly.
But,
What I wanted to
but
ask.
the Van Beeren argument can be used in 2 dimensions if you take it very anisotropic, even longer range in 1 dimension and nearest neighbor in the other.
It's very artificial somehow, counterexamples, but we use somehow Van Beeren proof to say that if in one direction you have long range and in the other one you have short range, then of course you can have Dobroshin states.
Very stiff.
And what about the isotropic case at low temperatures in 3 dimensions? What's the expected picture? So do you have Dobroshin states for some alphas or not?
Long range?
No values of alpha?
No, that's basically what you proved.
Yeah.
In 3 dimensions?
In 2 dimensions.
No, in 3.
In 3 dimensions, we can exclude for alpha large enough.
I think what happens in nearest neighbor probably also happens for long range.
Yeah.
So you don't exclude.
No, you don't exclude the interface states for long range.
Sorry. Let me think. Yes.
But do you have other states than the Russian state in 3D, like the tilted interface?
In dimension 4 it exists, but in 3D.
In dimension 3 with long range.
Yeah.
Yeah, I think.
Yeah. Maybe if it's there in 4D, you are right that it should be there in 3D long range.
Yes.
Yeah, it should be there.
Is it?
I don't know.
Okay. It's
but you're right.
To get arbitrary.
Yeah.
No, some angles, I would say, not all.
But once again, some features are.
But somehow this interface 111, Rick, is it, somehow, does it yield the proof that there exists a Dobroshin state in direction 111? No.
I would say it's more or less straightforward. But I'm not asking, so I...
You mean nearest neighbor? No.
Nearest neighbor.
111?
Yeah. In the direction 111?
No.
In 3 dimensions?
No.
It's rough.
It's rough.
Well, whether there is a proof that it is not.
That's correct.
There is, somehow zero temperature proof.
Yeah, zero temperature.
Yeah.
There's not impact.
But maybe excitations will somehow, tighten it.
Yeah, but it's not. Yeah.
I mean, you can construct counterexample to this kind of things. I mean, you can construct models in which the fluctuations at 0 temperature are bigger than at finite temperature. So you cannot expect a general argument by monotonicity or something.
The entropy energy arguments remind me, if I remember correctly, in case of the 1/r² potential in 1 dimension, David Taves came up with a prediction that there will be discontinuity in the magnetization based on an energy entropy argument. And Barry Seymour and Alan Sokal tried to turn this into rigorous statement without succeeding. The argument essentially stated that if there is no discontinuity, something very bizarre would happen, and therefore there should be a discontinuity. It so happens that this bizarre thing does happen. It's this KT-like phase there. So my question is, if you now have better grasp of the entropy energy arguments, is there a chance to see the Taoist discontinuity, which was proven by other means, through the energy
software tools is
argument?
a very nice question. Cannot answer now, but I have to think. Thank you.
Let's thank Loren again for